My name is Sotirios Paraskevopoulos. I work at KWR Water Research Institute. And today we'll talk about how we can use and harness artificial intelligence to tackle pathogen contamination events. Let's begin. So, in every pathogen contamination event, the preservation of health is a top priority of an emergency response mechanism. As we know, pathogens are difficult to detect and handle and can spread through water, either surface water or drinking water. And as we saw before, the future is becoming unpredictable. So we can have all sorts of natural events, floodings, earthquakes. We can have failures or malicious attacks in the drinking water network that can cause waterborne pathogen contamination events. And of course, the exposure to those contaminated water bodies can cause adverse health effects to the population. Therefore, we need to act fast, right? So, because time is very important in these situations, and we need to assess the threat. But to do that, we need information, all right? So we need to collect as much information as possible related to the contamination that we are facing. And what better place to start collecting this information than the scientific literature? But unfortunately, the situation is a bit different. As we all know, with the fast growing rate of the scientific publications, the information is often buried. And we know that experts sometimes cannot keep up with the latest developments in their respective field, and in our case, in the domain of environmental microbiology. Therefore, we need to find a way to get access to this information. And in our case, when tackling a contamination event, we need to find a way to get access to up-to-date and science-based information. So this is where the EU-funded project Pathocert kicks in, which stands for Pathogen Contamination Emergency Response Technologies. Here, the aim overall is to increase the coordination capabilities of the responsible authorities when tackling contamination events, to strengthen the situational awareness, response, and control options, and specifically, and this is related to today's topic, create an artificial intelligence-based approach to extract information on pathogen characteristics. Now, the conventional way of collecting information would be through manually searching the literature. And as you can imagine, this process is time-consuming, as one has to search through the plethora of publications, and it requires an expert that knows very well what to search and where, right? So what we proposed is an automated approach based on artificial intelligence that helps us extract faster the information, and it doesn't require an expert to do that. Now, artificial intelligence. AI in general is no stranger in the domain of biomedical sciences. Experts for more than 10 or 15 years already, they're using AI techniques, text mining techniques, to get information from electronic health records and randomized clinical trials. In those documents, usually the information is well structured within the document, which makes it easy to apply those techniques. Now, in our case, in the domain of environmental microbiology, things are a bit difficult because the information is often unstructured, which makes it difficult to extract this information. So this is what we asked ourselves. Can we apply the same techniques? Can we apply the same AI techniques to get this type of information from scientific publications? Or to put it in other words, can we take this piece of text here, which we see contains information on Legionella? You see the highlighted information, and it's sparse within the text. So can we go from this state to this state, where we see the same highlighted information, but this time nicely structured in a table? So that was the main question that we addressed. Now, a few things regarding our methodology. We decided to go with a proof of concept because we wanted to design a system that after we train it properly, it should be able to give us the desired results. So once we fed it with a scientific publication, it should be able to get us back the desired information. Here we see in this Venn diagram the different interconnections between the disciplines related to our methodology. So we have the information extraction techniques, natural language processing techniques, of course, and artificial intelligence. We focused on the waterborne pathogen Legionella because it's a well-known pathogen, often associated with outbreaks throughout the world, and we knew that we can find plenty of information in the literature. And then, of course, we had to specify what type of information we're looking, what exactly do we want to get from these publications. We see here that we have 7 information keywords, both qualitative and quantitative information about the incubation period or the associated symptoms on Legionella. So how do you design such a system? First, what you need to do is to collect your corpora. So collect the publications associated to Legionella in order to train your model later on. So this is what we did. We went to the search engine PubMed, and we collected 50 publications related to Legionella. Then the next step is to label the information keywords, which is basically the process where you assign the information keywords that I just showed to you to the respective words within the text. We see here an example of that process. And this is a very interesting and important process because this is basically how we train our model to be able to understand and identify what is important and what is not in the text. Very important. And then once we've done this, it's time to train and test our model. So train our model with the 50 publications so it can learn what is important and what is not, and then test it to see if it makes sense, if the extracted information makes sense. This graph here on the right basically tells us that the more publications you train your model with, the better your model accuracy on extracting the right information. Now, we go to the results section. So we trained our model, we tested, let's see if it works. And as we can see here, this is a bit technical, but I will just give you a brief overview. We have the precision and recall evaluation metrics, and what this table tells us is that basically we were able to train very well our model, and it's able to extract high quality and meaningful information. We see here on the right an example of it. That means that the model is trained well enough, and it was able to get us the right information for both qualitative and quantitative information keywords. That was very promising, right? And then we said, this is great, we have high evaluation metrics, but we need something more tangible. So we need to be able to assess the quality of the information. So what we did, we compared the system extraction with human extraction to see if it's actually the same. So this is what we did. We took 10 new publications, we fed it to the system that we had just trained, we let it do its magic, and then we did the same with a human expert. And then we brought this to a table as we see here. On the left, we see the system extraction, and on the right, the human extraction. And as you can all see, we have similar results, which means that, indeed, our model is able to get the information that we want, and it's behaving like a human would do. So that was very, very promising. Now, in our discussion and conclusion part, as I said, we had a very good performance on a set of 7 information keywords. We were able to train a model that is able to give us qualitative and quantitative information with high quality. The comparison with the human extraction substantiated this conclusion, as we saw that we had similar results. And overall, our methodology paved the way for a better understanding of the different processes, the specifics, and the boundary conditions associated on getting this type of information from scientific publications. Now, where can we use it? That's the basic question. Where can we apply this approach? Of course, we can perform meta-analysis. So if we're able to get, using this approach, to get many publications on different incubation time values, for example, we might be able to create a distribution curve. Or another example is to, if we're able to use this approach, to collect and categorize various transmission pathways of different pathogens and then create a database, which can be, of course, used for many other applications. And we can even expand this approach to different scientific domains, not only in our field, but in other domains. We can extract, for example, if we want to create a literature review or to collect information on inactivation rates at different temperatures, or, for example, in equations on inactivation kinetics, or to extract log removal values from various wastewater treatment processes. So we see that there are plenty of applications that we can have using the power of artificial intelligence. And of course, being able to extract high quality information in no time It's always helpful when someone is performing a systematic literature review. Now, finally, this is my last slide regarding the next steps. What we see here is the workflow of the Pathocert project. As I said, this is part of the Pathocert project. Today, I spoke about using AI to extract information on pathogen characteristics. Now, the next step would be to apply the same approaches or similar approaches related to AI, but this time extract information on health risks and control options from drinking water contamination events. And then the idea is to collect and curate this information, incorporate it into a decision support system that will help us assess the threat and propose control options for a contamination event. And we believe that this particular step, the second step, so being able to get information from drinking water contamination events from the past to see how others have assessed the situation or what were the health risks associated with a contamination event can be beneficial for the water utilities because it can provide them with an additional layer of information and help on decision-making processes when it comes to tackle pathogen contamination events. Thank you very much.
Well, thank you, Sotirios, for a very interesting presentation. I also see a risk here of future PhDs getting a bit lazy because they can just do their literature research via your AI module. But well, it's a bit different than when I think back, even going physically to a library when I was in that stage. So things change rapidly. I can imagine there are some questions from the audience. Yes?
Yeah, Oscar Alvarado. Thank you very much for the great presentation. I'm curious about the platform or the software that you used to implement this AI and to get all of this information. Thanks.
Yeah, thank you for the question. Right now, there's no platform, but indeed, it's in the plans, part of the Pathocert project, to create a platform with a friendly user interface where there, as I said, this process, we will collect this information and then create a decision support system that can help us assess the threat during those stages. But at the moment, there's no platform. But it will be. So stay tuned in the Pathocert project.
Just the crucial bit on a search is usually how you can make a user interface to allow the person to articulate in a detailed way the search and how it links to whatever algorithm you're using. So how would you implement, if it's a, with your AI system, how would you implement a very detailed and circumvented search criteria?
That depends on the use, of course. In our case, we just wanted to see, first of all, if it works, if we can indeed use AI to extract this type of information based on the set of these 7 information keywords. But of course, we can use different keywords depending on the end use. So it really depends on what exactly is that you want to extract. There's no certain way of using criteria for that purpose. I don't know if I answered your question. So if you want to...
usually there is a lot of black box algorithm in AI nowadays. Things like deep neural networks.
Is
that what you're using?
Yes, exactly. Okay, we're using deep learning techniques, supervised and unsupervised techniques in combination in hybrid approaches, because it's really important, and that was one of the difficulties that I had in the beginning. We went with machine learning approaches, but then we realized that it's not enough because our system is not smart enough, because getting the right information is more difficult. The information is really complex. There are so many ways that scientists nowadays write their publications, so there's no pattern that you can follow. So you need to be able to get to use an approach, deep learning approach, that is able to understand the context of a sentence in order to extract the right information. So we use deep learning techniques indeed.
Okay, yeah. Thank you, Sotirios.
I
Maybe
thought there were
was
some
another question.
other questions.
Oh, yeah, I see. Still one. We can still do one question.
Okay, thanks for your presentation. I understand that you developed your model and applied the model on a scientific database. It was Scopus or PubMed?
PubMed, yes.
Can you also apply it on a broader database with the grey literature? Because there's a lot outside the scientific world, and then you miss that. So is that also a possibility of your approach?
Of course, it can be applied in grey literature. Of course, you have to make sure that the quality is adequate always. But indeed, you can apply it to other databases. It's just that we chose PubMed because it was easier to get access to information related to Legionella.
Yeah, I had a similar question like that. It's also maybe for future for you. It's like PubMed is not accessible for everyone. So I would really see it if it's possible to do a test on just open journals, open access journals, compared to also paid journals, to see if there are large differences. Then you can get a broader use of your system.
Yes, of course.
Okay.
Thank you very much.
Thank you, Sotirios.